is Sebastian Lee. I'm here working in the broader group in the chemistry department with my mentor, Hunter Nielsen. I'm going to be a second-year CCS chem major next year, and today I'm talking to you about the catalytic activity of vanadium oxide nanoclusters. So, what's the point of this? Why are we even doing this in the first place? Well, one of the most interesting things that I found doing this research is that these small clusters, things on the nanoscale, so let's say about 7 atoms, exhibit different properties than they do in the bulk material. So for example, let's go with a piece of gold. We have a piece of gold in our hands, it's not going to do anything. It's relatively inert, we use it for jewelry. But if you bring it down to maybe 7 atoms, it actually has catalytic properties. And these properties we can try to understand. But then one of the magical things about this is that you add one more atom to it and then it goes away. So what we're trying to figure out is the same thing except now with vanadium oxides, which also exhibit catalytic behavior. And we want to fundamentally understand these properties, and then eventually we can have other people apply them and make these materials that actually have these catalytic properties by cluster deposition. So by landing these ions or lining these clusters onto a surface, and now makes the surface catalytically active, which can be used in the industry. So what's our first step? Well, we want to be able to synthesize all these vanadium oxides. There's a multitude of them. Industry uses them in their reactions, such as the oxidation of SO2 to SO3, which is a very important step in the synthesis of sulfuric acid. The problem is they just have a bunch of vanadium, oxidize it on a surface, and they know it works, but they don't know which vanadium oxide works, and that's what our goal is. And we can actually, for the VXOY, we can for sure determine what the X is and what the Y is. We can control that. So once we have it, once we've created these vanadium oxides, we want to deposit them onto a surface, in this case titanium oxide, and run experiments. Once we have it, we want to test the catalytic behavior of them. And we use this studying a simple reaction, actually, is the partial oxidation of methanol to formaldehyde, which is shown right here. We have the methanol, which is exposed to the surface, and then we see if formaldehyde and water comes off, with VXOY as our catalyst. So this is my last setup right here that we've been using this entire summer. I'm going to talk to you about 4 different methods that we use here. The first is the laser ablation. And this is when the laser comes in and hits our cluster source. In this case, that's a vanadium rod about this long. Moves up and down and in a circle to provide even coverage for our laser, because our laser is strong enough to burn a hole through it, which then would burn a hole through our apparatus and then break vacuum and cause lots of problems. So once we have the laser hitting the sample, it produces a gaseous vanadium. And then we introduce a gas of argon and oxygen, which stimulates the growth of vanadium oxides. This is still in gaseous form, and as the ions travel through and reach the magnet, the next step is massively selecting our vanadium oxides. And this is how we control the VX and the Y in our sample. So how it works is that we have this magnet here that can be controlled. The way that works is that by varying the strength of the magnetic field, we can determine which ions get through the flight tube based on their mass. And all this information is collected at the movable detector, and so we run through a bunch of different magnetic field strengths, and then we see what ions come through, and this creates this graph we have right here. And this is how, these are all the different ions that we've made, and we've determined what each of these peaks are just by empirical evidence. So what we have here is these 2 largest peaks are VO and VO2. Those have both already been done in our group, so we've been going onwards to different vanadium oxides. Both of those did not exhibit catalytic behavior, so we're hoping to find some more in the future experiments. The ones we've been working on right now are V206 and the V304, you can see over on the right. We've been focusing on those mainly just because they have relatively larger peaks in this case, so we've been creating more ions. We want to come back and visit the ones in the middle, the lower peaks, but right now we can't just because they're relatively weak. So we have to optimize our parameters to make them stronger. But as you can see, I have the V304 and the V207 on the same peak, and that's because they're actually very close in mass together that we can't determine from this graph alone which one is being formed. But from our friends in other labs, they said from theoretical evidence that the V304 would be more favorable. Next we have our deposition, and this is what we have right here in the deposition chamber. This is when we deposit our sample. But to do this, we need to soft land these ions. These ions are moving extremely fast, and when they hit the surface, they're either going to bounce off or cause structural problems when they hit. Maybe losing all catalytic behavior that we could have seen. So the way we do this is we apply a voltage to our sample. The way this happens is that this voltage repels the positive charge on the ions, and repels it just enough to slow them down and hit the surface, but not enough to knock them away. And the way we figure out what voltage to apply is by running through a bunch of different voltages, which is what we have down here. The vertical column shows our signal strength, so it's around 160 picoamps. And then as the bias increases, our signal slowly drops off. You can see the range between the two is about 30 volts, so it's a very small area where our signal actually drops off. And this is when our graph here shows us what biasing voltage we need to set it at to soften the ions. At first you would think, let's set it about halfway. We're going to get most of them soft landed on, some will get knocked off, but it'll get the job done. The problem is it loses half of our signal. And with the small peaks that you saw, the low amount of ions that we're making, this makes deposition time run up to like almost 8 hours. So we thought about it, and we've talked to other people about it, and we actually have a different spot we can use. This spot right here, we call the leading edge. This is, as you can see, our signal's still about all there, but this is enough to slow them down to actually soft land. And so this actually really helps in the time we take to run depositions. So finally we have TPD, or temperature programmed absorption. This is actually the very exciting step where we test catalytic behavior. What we do is we expose the surface to methanol, and then we move it to a mass spectrometer and we heat it up. And then based on the temperature it is at, we look for the different species, in this case formaldehyde and methanol, and this gives us this graph right here. So you can see at the different temperatures we see we see formaldehyde in the red and the methanol in blue, and we see what comes off at certain temperatures. And you can see this noticeable peak for the red one, for the formaldehyde, and the 500 to 700 K temperature. This is actually extremely exciting for us. This shows that this possibly could be catalytic, in this case V3O4. We have to run additional experiments, run some more, see if we can do it again, replicate the results. But this looks very promising, and it's just a first step in the future experiments. So what we have so far is that we've successfully deposited V2O6 and V3O4. We've run temperature programmed absorption on both of these, and you just saw the graph for V3O4. And as you know, it looks like it could possibly be a catalyst, which is what we're really excited about. Although, continuing on, you saw all those other ions that we were able to create as well. We want to run through each of those and see which ones work as catalysts, which ones don't, which ones work maybe as a better catalyst, and which ones have only slight catalytic behavior. Then we're going to go to X-ray photoelectron spectroscopy. This will actually tell us what's on the surface. So we were questioning about the V3O4 and the V2O7. This will tell us exactly what's on our surface, if it was really V2O7, or if it really was V3O4, or maybe a combination of both. Finally, we like to image the surface with scanning tunneling microscopy. This will just show us how the ion is oriented on the surface and just what it looks like. So I'd like to acknowledge the Barada Group. Thanks for coming to listen to my talk. Thank you, EUREKA, for the funding, NSF for funding our group, CNSI, and I'm into Hunter Nielsen for helping out.